Welcome to the world of television. This is the first part of the You Can Do video series designed to teach you about the inner workings of the color television receiver. In this video, you will gain an overall view of how the television receiver is able to reproduce a complex signal into a moving work of art. You will examine many of the common functional blocks necessary to achieve the illusion of a moving picture. By the time you are finished with this video, you will have formed a solid foundation from which to build upon as you complete your future You Can Do video lessons in television technology. As the transmitted RF signal is received by the color television receiver, it is divided into four basic forms of information: sound, image, color, and control. As you can see, there are timing circuits contained within the television receiver which derive information from the broadcasted signal. Here you see a composite video signal waveform. This video signal contains both phase-modulated and amplitude-modulated signals. The composite video signal also contains timing pulses which are used by the television receiver to synchronize the information being received. You will learn more about this waveform in a later You Can Do video. Now let's examine the color television receiver and see how it works. You are looking at a block diagram of a typical color television receiver. It contains all the circuits normally found in today's standard color television set. Even though today's modern TVs appear to have less components, they must still have the same functional blocks that are being shown here. Due to today's high technology, many of these blocks are commonly found in a single IC package. We will begin with the tuner stages, since the transmitted signal will enter these first. Notice that there are two tuner stages located in the color television receiver. One is labeled UHF, and the other is labeled VHF. The primary function of the tuner stage is to select the desired TV channel from the various RF signals being inputted to it. Next, it amplifies the weak RF signal and changes the frequency of the incoming RF signal to a lower intermediate frequency value. The UHF tuner is the ultra-high frequency tuning device in the color TV receiver. It is designed to receive channels 14 to 69 from the television broadcast bandwidth. The VHF tuner is the very high-frequency tuning device in the color TV receiver. It is designed to receive channels 2 to 13 from the television broadcast bandwidth. Defects in the tuner stage can cause a number of problems with the video image, color, and sound reproduction in the television receiver. For example, the raster on the screen may be good, and yet the picture and sound may be missing altogether on all the channels. Or the raster may be good, and the picture and sound may be missing on just some of the channels. Defects in the tuner stages will also cause the picture to become weak or snowy on all the channels, and yet the sound will be normal. The picture could also be weak or snowy on just a portion of the channels, while the rest of the channels are normal. Tuner defects can also cause the color to be missing or faded on just some or all of the channels. Defects in the tuner can also cause the picture and sound to be located at different fine-tuning settings. As you can see, tuner defects can create a number of symptoms within the receiver. These defects may be caused by a component which has changed value, a failed component, poor solder joints, or poor connections at the input of the tuner stages. We will now pause for a short review of the material just discussed. The televised transmitted RF signal contains four basic forms of information: image, color, sound, and synchronizing control pulses. The tuner consists of two major sections, the UHF, or ultra-high frequency stage, and the VHF, or very high frequency stage. The UHF stage is designed to receive channels 14 to 69 of the broadcast channel bandwidth. The VHF stage is designed to receive channels 2 to 13 of the broadcast channel bandwidth. The tuner section has three main functions. First, it selects the desired channel. Second, it amplifies the weak RF signal. Third, it converts the RF signal to a much lower intermediate frequency value. Defects in the tuner stage can cause problems in the image, color, and sound reproduction within the television receiver. This concludes review number 1. At this time, you should stop the video and complete section A in your student workbook. Now let's examine the automatic fine-tuning stage in the color television receiver. The automatic fine-tuning, or AFT as it is often called, is used to automatically lock in the best possible reception for the channel selected. Since fine-tuning is very critical in a color receiver, this stage is rather important. Notice that the AFT stage is fed by the video IF detector section. The video IF detector stage outputs a 45.75 MHz AC signal into the AFT section. This signal is used to control the output of the automatic fine-tuning stage. The output of the AFT stage is then fed into the VHF section. The signal actually goes to the VHF tuner oscillator circuit, where it is used as a correction voltage to change the frequency of the oscillator circuit, so that tuner is forced to lock in on the best possible reception of the incoming signal. This then allows the automatic fine-tuning stage to control the fine-tuning within the television receiver. There may be times when the AFT stage is labeled as an AFC stage. The AFC stands for Automatic Frequency Control. In either case, the function of the stage remains the same. Now let's examine the video IF detector stage and see what it does. The video IF detector stage provides most of the signal amplification of the incoming signal. It also provides the selectivity and bandpass characteristics necessary to minimize the interference caused by adjacent channel frequencies. This stage also converts the high-frequency IF signal into a composite video waveform. Notice that this stage also provides an output signal to the sound IF detector stage located in the first part of the audio portion of the television receiver. Even though the video IF detector stage is represented by a single block in the block diagram, it actually consists of 3 or 4 video IF amplifier stages, a video detector circuit, and a sound IF detector circuit. As you can see, this stage is responsible for several functions within the color television receiver. Since the video IF detector stage processes the video image, color, and sound portions of the signal information. Defects in this stage will create a variety of symptoms within the color receiver. These symptoms include all those which can be produced by defective tuner operations, as well as a few others. For example, defects in this stage can produce sound bars in the video picture, a buzzing sound in the audio output, poor vertical or horizontal synchronization, or poor color fit between the video image and the color. Defects in the video IF detector stage are commonly the result of misalignment, components changing value as they heat up, or changes in the total amplification of the IF amplifier sections contained within the stage. Now let's examine the audio section of this color television receiver. As you can see, the audio section of the color television receiver consists of 4 major sections. These are the sound IF detector stage, which converts the high-frequency audio IF signal to a much lower 4.5 MHz IF signal. This is the portion of the signal which carries the audio information. The second section is the sound IF amplifier stage. This stage is designed to boost the 4.5 MHz signal to a workable level. The third section is the sound detector stage. The sound detector stage converts the sound intermediate frequency signal into audio frequency signals. The fourth section is the audio amplifier stage. The function of this circuit is to boost the audio signal to a level sufficient to drive the speaker at the output of the stage. The audio stages in the color television receiver are at times referred to as the sound strip. The audio section in the TV receiver is very similar to that of a standard FM radio receiver. This is due to the fact that the audio information is in the form of a frequency modulated signal. Even though the audio stages in the television receiver are very similar to those found in an FM radio, there are some differences. For example, the FM bandwidth allowed for audio information in the television receiver is only 50 kHz as opposed to the 150 kHz allowed for a commercial FM radio station. The television sound system also has an advantage of being tuned to only one frequency. Defects in the audio stages are easy to recognize. They can occur in 4 different categories: no sound, weak sound, distorted sound, and a buzz in the sound. In each case, the video image and color will be normal. The symptoms will only show in the audio reproduction portion of the receiver. We will now pause for a short review of the material just discussed. The automatic fine-tuning circuit is used to synchronize the incoming signal for the best possible reception of image, sound, and audio. The video IF detector stage provides signal amplification, selectivity, and bandpass characteristics required for minimizing adjacent channel interference. It converts the IF signal into the composite video signal, and it outputs the frequency bandwidth necessary for the audio reproduction portion of the television receiver. The video IF detector stage will contain 3 or 4 video IF amplifiers, a video detector circuit, and a sound IF detector circuit. The audio section of the television receiver will consist of 4 major stages. These are the sound IF detector stage, sound IF amplifier stage, sound detector stage, and the audio amplifier stage. The audio information contained in the broadcasted television signal is frequency modulated. Therefore, Many of the circuits used in the audio section will be similar to those found in a standard FM radio receiver. This concludes review number 2. At this time, you should stop the video and complete section B in your student workbook. Here you see the heart of the video image circuitry. The signal produced at the output of the final amplifier stage in this string is known as the Y or luminant signal. The Y signal is responsible for the video image which is shown on the TV screen. The Y signal controls the brightness levels within the picture tube, thereby producing an image ranging from black to white. Notice that the video image portion of the color television receiver consists of 4 major blocks. They are the first video amplifier stage, the second video amplifier stage, the delay line stage, and the video output amplifier stage. The function of the first video amplifier stage is to amplify the composite video signal, then route the boosted signal into the second video amplifier stage, the chroma bandpass amplifier stage, the burst amplifier stage, and the automatic gain control stage. The second video amplifier stage provides additional boost to the video signal and receives vertical blanking signals from the vertical section of the color television receiver. It is not uncommon to find as many as 5 amplifier stages in the video amplifier string. The next part of the video image string is the delay line stage. The purpose of this stage is to delay the Y signal so that it arrives at the picture tube at the same instant that the color signal information arrives. This stage is necessary due to the fact that the Y signal has fewer stages to pass through than does the color signal. The final stage in this string is the video output amplifier. This amplifier stage provides sufficient boost to the video signal so it can drive the control grids located within the picture tube. Video signal levels at the output of this stage can be as high as 150 volts peak to peak. This value, of course, would depend upon the type of picture tube being used. Defects in the video amplifier section will seldom affect the color, sound, or raster on the TV screen. About the only time you will encounter a problem with both the color and video image from the video amplifier string is when there is a defect in the first video amplifier stage. Now let's examine the AGC sync separator stage. AGC stands for Automatic Gain Control. This block actually functions as 2 separate stages within the AGC block. We will examine them one at a time. The automatic gain control portion of this stage generates a DC voltage that is proportional to the strength of the inputted RF signal. This DC correction voltage is used to control the gain of the IF amplifier sections. The AGC stage is designed to maintain the synchronization pulse peaks at a constant level, regardless of changes in the input signal. By feeding its signal into the VHF tuner stage and video IF detector stage, it is able to reduce the input signal to the proper magnitude before it is fed into the first video amplifier stage. The sync separator portion of this stage is designed to remove the sync pulses from the composite video signal. These sync pulses are then used as timing signals and are fed into the vertical and horizontal deflection circuits. If the AGC signal is too low, a negative picture may appear, as well as a buzzing sound in the audio output. If the AGC signal is too high, the video image and sound may be weak or non-existent. We will now pause for a short review of the material just discussed. The video image is produced by the Y signal. The Y signal is also commonly referred to as the luminance signal. The four primary blocks which make up the Y signal portion of the television receiver are the first video amplifier, the second video amplifier, the delay line stage, and the video output amplifier stage. The primary function of the first two video amplifier stages is to boost the video signal to a level sufficient to feed the video output amplifier stage. Since the Y or luminance signal has fewer stages to pass through than does the color signal, a delay becomes necessary so that the color and luminance signals reach the picture tube at the correct time for proper color image reproduction. Depending upon the type of picture tube being used, the output of the video output amplifier stage may be as high as 150 volts peak to peak. AGC stands for Automatic Gain Control. The function of the AGC stage is to maintain the synchronization pulse peaks at a constant level regardless of changes in the input signal. This concludes review number 3. At this time, you should stop the video and complete section C in your student workbook. Now let's examine some of the stages used in the color section of the standard color television receiver. As you can see from this block diagram, there are a number of stages contained within the television receiver for the primary purpose of reproducing the color back into the luminance signal. We will begin with the chroma bandpass amplifier stage. The primary function of this stage is to amplify and separate the color or chrominance signal from the composite video signal which was fed into it by the first video amplifier stage. The chrominance signal is then fed into the X and Z demodulator stages. The overall average bandwidth of this bandpass amplifier is 1 MHz. The color killer stage has the ability to turn on or turn off the bandpass amplifier stage. When the color burst is present in the composite video waveform, the color killer stage will turn the chroma bandpass amplifier stage on. If the color burst is not present, as in a black and white transmission, the color killer stage will hold the chroma bandpass amplifier stage off. The phase of the chrominance signal is very critical for proper color reproduction. Any deviation from the phase of the subcarrier at the TV broadcast transmitter will result in a change of color at the television receiver. Since even a slight variation of the carrier from the reference phase will cause a change in color, it becomes necessary to use signals which synchronize the reference signal to the carrier signal. Here you see the stages responsible for the synchronization of the color signal. They include the burst amplifier, color phase detector, 3.58 MHz color oscillator, and the oscillator control stage. The color burst amplifier is triggered on and off by pulses coming from the horizontal output amplifier stage. Each time the horizontal amplifier pulses the color burst stage, it turns it on. This causes the burst amplifier stage to output 8 cycles of color burst. The 8 cycles of color burst are then fed into the color phase detector stage. The frequency at the output of the color burst stage is 3.579545 MHz. Most of the time, the frequency of the color signal is referred to as being 3.58 MHz. The chroma phase detector stage compares the phase difference between the color burst from the burst amplifier with that of the 3.58 MHz signal generated by the 3.58 MHz oscillator stage which feeds into it. If a phase difference exists between these two signals, a DC correction voltage is generated and fed into the oscillator control stage. This causes the oscillator stage to synchronize with the color burst signal. The chroma phase detector stage also generates a signal which disables the color killer stage. As long as this signal is being applied to the color killer stage, it remains disabled and the chroma bandpass amplifier remains activated. The primary function of the color oscillator stage is to provide the 3.579545 MHz signal, which is used as a phase reference to demodulate the chroma sidebands. This stage actually restores the subcarrier that was suppressed at the transmitter. Here you see the control stage for the 3.58 MHz color oscillator. The oscillator control stage receives an input signal from the color phase detector stage. It converts this DC correction voltage into a variable reactance that is used to control the color oscillator stage. Now let's examine the demodulator stages contained in a color television receiver. As you can see, there are two demodulator stages. Both of these stages are required in the receiver to reverse the process of the two balanced modulators at the transmitter. There are several types of demodulator circuits being used in color television receivers. Here you see the two most common, the X demodulator and the Z demodulator. Both the X and Z demodulator stages are fed the same chrominance signal from the chroma bandpass amplifier stage. Both stages are also fed from the color oscillator stage. The X and Z demodulator stages are designed to operate at any desired axis with respect to the phase of color frequency. The demodulated signals can then be combined into proper proportions to produce the different color signals that are required to properly drive the picture tube. The final three stages we shall examine in the color section of the television receiver are the B-Y, G-Y, and the R-Y amplifier stages. The B-Y, G-Y, and R-Y amplifier stages perform two major functions. First, they act as a matrix to convert the X and Z demodulator outputs into the color difference signals. Second, they amplify the color information to a level sufficient to drive the color guns located in the picture tube. Notice that the B-Y amplifier stage and the R-Y amplifier stage are fed respectively with the outputs from the Z demodulator stage and the X demodulator stage. The B-Y and the R-Y stages are also fed from the horizontal blanking amplifier stage. The demodulator stages are used to provide the color difference information to the proper amplifier sections. The input from the horizontal blanking amplifier is used to synchronize this color information. You should also have noticed that the G-Y amplifier stage is being supplied signals from each of the other two color amplifier stages. The G-Y stage will matrix the color information received from these other two sections and produce the signal necessary to drive the amplifier stage for the green color gun located within the color picture tube. This stage also receives synchronizing pulses from the horizontal blanking amplifier stage. The demodulating and matrixing of the color information is somewhat complex and will be covered in detail in a later You Can Do video. We will now pause for a short review of the material just discussed. The primary function of the chroma bandpass amplifier is to separate the chrominance information from the composite video signal. It also amplifies the color information. The color killer stage is used to control the operation of the chroma bandpass amplifier section. The color killer has the ability to turn the bandpass amplifier on or off. The color burst amplifier outputs 8 cycles of 3.579545 MHz color signal each time it is triggered on by the horizontal output amplifier stage. The color phase detector stage compares the phase difference between the color burst signal and the 3.579545 MHz reference signal generated by the color oscillator stage. The demodulator stages are used to produce an output that is directly related to the amplitude and phase of the chrominance signal. The B-Y, G-Y, and R-Y amplifier stages are used to produce the blue, green, and red color information to the color guns located in the color picture tube. This concludes review number 4. At this time, you should stop the video and complete section D in your student workbook. In this portion of the video, you will examine the stages necessary for proper horizontal and vertical synchronization of the luminance signal when it produces an image on the television receiver screen. We will begin with the stage responsible for the vertical synchronization of the video image. Here you see the vertical deflection and output amplifier stage. This stage performs 2 primary functions. First, it generates a sawtooth waveform and provides sufficient power to drive the vertical deflection yoke. Second, it provides retrace blanking pulses, timing pulses for the convergence stage, and timing pulses for the pincushion stage. The vertical deflection portion of this stage is generally a blocking oscillator. The output frequency of this oscillator circuit is 59.94 Hz and will be a sawtooth waveform. The sawtooth signal produced by the blocking oscillator is fed into the output amplifier. The primary purpose of the output amplifier is to supply sufficient power to drive the yoke coil which is mounted on the neck of the picture tube. Now we will examine 3 of the stages required for proper synchronization of the horizontal signal with respect to the image being scanned onto the face of the picture tube. These 3 stages are the horizontal output amplifier, the horizontal oscillator and automatic frequency control stage, and the horizontal blanking amplifier. We will begin by examining the horizontal output amplifier stage. The horizontal output amplifier stage is probably one of the most important stages in the color television receiver. This stage provides signals for many of the other stages located within the system. It drives the deflection yoke to produce the horizontal scanning. It provides synchronization pulses for the automatic gain control, blanking amplifier, color killer, and burst amplifier stages. The horizontal output amplifier also provides the AC voltages required to operate the high voltage rectifier stage and the focusing rectifier stage. This stage also outputs signals into the pincushion and convergence circuits. As you can see, this one stage is responsible for the proper operation of many different stages located within the color television receiver. The primary function of the horizontal oscillator AFC stage is to compare the horizontal sync pulses with the signal produced by the horizontal oscillator contained within this stage. The horizontal oscillator then outputs a DC error voltage that is dependent upon the frequency error between the oscillator output and the horizontal sync pulses being produced by the AGC sync separator stage. This stage generates a sawtooth waveform with a frequency of 15,734 Hz. The horizontal blanking amplifier stage performs one key function. It is used to turn off the video output amplifier and color amplifier stages during the horizontal retrace interval. Now we will examine 2 more sections used in the horizontal circuitry. They are the damper stage and the deflection yoke. The damper stage and the horizontal output stage work together to provide the horizontal scanning on the interface of the picture tube. The primary function of the damper circuit is to provide the B+ boost voltage, and it is responsible for the deflection on the left side of the raster being produced on the screen. The deflection yoke is basically an electromagnet made up of coils of wire. The deflection yoke will be located on the neck of the picture tube. As current is passed through the deflection coils, a magnetic field will be produced inside the neck of the picture tube. This magnetic field is used to control the horizontal and vertical scanning sequences of the electron beams being generated by the color guns at the end of the picture tube. As you can start to see, the deflection yoke is responsible for both the horizontal and vertical scans being produced as a raster on the picture tube. Now let's examine two more stages used in the deflection portion of the color television receiver. These are the pincushion circuit and the convergence circuit. When the larger picture tube became popular, the top, bottom, left, and right sides of the picture tube would tend to bow inward toward the center of the picture tube screen. This defect was known as pincushioning. To overcome this defect, the pincushion circuit became necessary. The pincushion circuit automatically increases the horizontal width and vertical size of the raster in the affected regions to overcome this defect. The pincushion circuit accomplishes this by modulating the amplitude of the horizontal deflection current and by forcing the vertical deflection current to pulsate in amplitude at the horizontal scanning rate. The convergence circuit is used to assure that the three electron beams being produced by the three color guns in the neck of the picture tube are properly aligned so that all three beams strike the exact same place over the entire face of the tube. There are normally 12 adjustments located on the convergence board. We will now pause for a short review of the material just discussed. The vertical deflection output amplifier stage performs two primary functions. First, it generates a sawtooth waveform of sufficient power to drive the vertical deflection yoke. Second, it provides retrace blanking pulses and timing pulses for the convergence and pincushion sections. The horizontal output amplifier stage is electrically connected to many of the various stages of the color television receiver. It has signals going to and from the high voltage hold down, regulator, and damper stages. It also receives a signal from the horizontal auto frequency control stage. This stage also supplies signals to the pincushion, convergence, deflection yoke, high voltage rectifier, focus rectifier, horizontal blanking amp, color killer, burst amp, and sync separator stages. This is a very crucial stage in the color television receiver. The horizontal oscillator AFC stage is responsible for comparing the inputted horizontal sync pulse with the signal being generated within the oscillator stage. The output of the oscillator stage is then fed into the horizontal output amplifier section. The horizontal blanking amplifier stage is used to disable the video output and color amplifier stages during the horizontal retrace intervals. The deflection yoke is made up of coils of wire and is located on the neck of the picture tube. Its primary function is to control the electron beams being emitted by the color guns to ensure a proper scanning sequence on the face of the picture tube. The pincushion circuit is used to overcome a problem called pincushioning. Pincushioning is when the top, bottom, left, and right sides of the picture bow inward toward the center of the screen. The pincushion circuit increases the horizontal width and vertical size of the picture to overcome this defect. The convergence circuit is used to properly align the three color guns so they all strike the same part of the interface of the picture tube at the same time. This concludes review number 5. At this time, you should stop the video and complete section E of your student workbook. In this portion of the video, we will first examine the high voltage section of the color television receiver. We will examine the high voltage rectifier stage, high voltage regulator stage, the high voltage hold-down circuit, and the focus rectifier stage. Then we will end this portion of the video with information about the low voltage power supply section. We will begin with the high voltage rectifier stage. The primary function of the high voltage rectifier stage is to rectify the high voltage AC signal being fed into it from the horizontal output amplifier stage into a high DC voltage. In some color receivers, this voltage may be as high as 35,000 volts. This high DC voltage is then fed into the second anode of the picture tube. The heart of the high voltage rectifier stage is basically nothing more than a special high voltage half-wave rectifier diode. The high voltage regulator circuit is used to assure that the second anode voltage remains constant under different brightness conditions. Notice that the high voltage regulator circuit uses a closed-loop system. It basically monitors the high voltage output of the horizontal output amplifier stage. If the voltage on the amplifier stage becomes too high, the high voltage regulator will cause it to reduce the magnitude of the voltage. Or, if the output of the amplifier is too low, it will cause the output of the amplifier to increase the magnitude of the signal. There are 4 common high voltage regulator configurations in use today. These are the shunt regulator, pulse regulator, closed-loop diode regulator, and the closed-loop voltage-dependent resistor regulator. The government issued a number of regulations designed to protect the public from excessive radiation being emitted from television picture tubes. This brought about the advent of the high voltage hold-down circuit. The primary function of this stage is to reduce the high voltage output in the event of a malfunction in the high voltage stages, which would result in the high voltage becoming excessive. The focus rectifier stage is generally found in the older television receivers. The output voltage from this stage was typically 20% of the second anode voltage value. If the magnitude of the second anode voltage was 20,000 volts, then the output voltage from the focus rectifier stage would have been approximately 4,000 volts. The primary function of this stage was to assure that the image being shown on the screen was clear and crisp. The low voltage power supply is responsible for supplying sufficient DC voltages at the proper amplitudes to the various stages located within the television receiver. This stage also supplies the energy required to drive the heating element located within the picture tube. This power supply has all the elements of a standard DC power supply. It will typically contain a transformer, rectifiers, filters, and regulator circuits. The demand for current from this stage will normally range from 400 to 1500 milliamps. The voltage levels being produced by this stage will range from a few volts to over 300 volts DC. We will now pause for a short review of the material just discussed. The primary function of the high voltage rectifier stage is to convert the high-voltage AC signal from the horizontal output amplifier stage into a boosted DC potential. This DC voltage is then fed into the second anode of the picture tube. The high-voltage regulator stage is used to maintain a constant voltage value for the second anode in the picture tube. The high-voltage hold-down stage is responsible for reducing the high-voltage output in the event that a malfunction occurs in one of the high-voltage stages, which would result in the anode voltage becoming excessive. The focus rectifier stage is commonly found in older television receivers. This stage is used to keep the electron beams being emitted by the CRT guns from spreading and causing the picture to look out of focus. The low-voltage power supply converts the incoming AC line voltage into direct current voltage levels necessary to drive the various stages used in the television receiver. This stage also supplies the current required for the heating element in the picture tube. This concludes review number 6. At this time, you should stop the video and complete section F in your student workbook. In this final segment of the video, we will review the primary sections of the color TV receiver. Instead of depicting the color television receiver as a series of operational stages, as we have done to this point, we will break it down into its basic sections. Here you see a very basic structure of a color television receiver. Notice that it contains a front end, detector circuits, audio circuits, luminance circuits, color circuits, high voltage, and synchronization circuits, and of course the cathode ray tube, or picture tube as it is more commonly called. As you recall, the front end of the receiver contains the UHF and VHF stages. This section of the television receiver performs 3 basic functions. First, they select the desired channel from the various RF signals being inputted into them. Next, they amplify the weak RF signals to a usable level. And finally, this section changes the frequency of the incoming RF signal to a lower intermediate frequency value. Basically, the front end is the tuning section of the television receiver. The detector section refers to all stages responsible for the detection and separation of the audio, luminance, color, and synchronization information contained in the received television signal. Even though the primary function of this section is to separate the received information into its basic components, it also amplifies the signal and converts it into a composite video waveform. The audio section is responsible for converting the 4.5 MHz signal, which is fed into it, into an audio frequency signal which has sufficient power to operate the speaker system in the television receiver. The audio stages operate on frequency modulated signals. Most of the newer color television receivers will contain stereo circuitry. For additional information about frequency modulated circuits, you should review the You Can Do videos FM Part 1 and FM Part 2. The luminance section is responsible for the black and white reproduction of the televised signal. The luminance signal is also commonly referred to as the Y signal. The output of the luminance section is fed into the cathode ray tube, where it controls the brightness levels of the video image. These brightness levels range from solid black to solid white, as well as the various shades of gray between these two extreme points. The color section of the television receiver is responsible for reproducing the correct hue and color saturation of the received signal. It must also time the color signal to the luminance signal so that the two signals are produced at the exact same instant inside the picture tube. In reality, this timing sequence is controlled by the delay line stage located in the luminance circuitry. The color signal is commonly referred to as the chrominance signal. The frequency of the chrominance signal is 3.579545 MHz and is a phase-modulated signal. The synchronization section is responsible for the proper timing of the horizontal and vertical deflection circuits in the television receiver. The vertical deflection circuitry will operate at 59.94 Hz. The horizontal deflection circuitry will operate at 15,734 Hz. Basically, the video image you see on the face of the picture tube is a result of the electron beams being emitted from the color guns within the picture tube, a constant left-to-right, top-to-bottom scanning sequence on the face of the CRT. By synchronizing and interlacing the scanned images at approximately 30 times per second, the illusion of a moving picture will appear on the face of the picture tube. The high voltage section is responsible for providing the high DC potential required to operate the cathode ray tube. Extreme caution must be maintained when troubleshooting on or around this lethal circuitry. Voltage levels as high as 35,000 volts may be present in these stages. Specially designed test equipment is required when working in the high voltage circuits. The CRT, or cathode ray tube, is nothing more than a specially designed vacuum tube. The color CRT will contain 3 electron guns, one each for red, blue, and green. The CRT will also contain various control grids used for controlling the electron beams being emitted by the color guns. Beyond the neck of the picture tube, the CRT will have an aquadag coating which will extend to, but does not touch, the phosphorus coating on the face of the screen. The aquadag coating is used to help accelerate the electron beams before they strike the phosphorus coating on the inner face of the screen. A mask is also placed inside the CRT, which has about 400,000 holes in it. All 3 electron beams must pass through the same hole at the same time for proper operation. The phosphorus screen actually consists of small dots of phosphorus which are designed to line up with the holes in the mask. You will learn more about the picture tube in a later You Can Do video. We will now pause for a short review of the material just discussed. The front end section of the television receiver is used to select and amplify the weak incoming RF signal. Detector circuits are necessary to separate the audio, luminance, color, and sync information from the televised signal. The audio section is used to reproduce the audio portion of the televised signal. The luminance section is responsible for reproducing the video image onto the face of the picture tube. This section processes the black and white portion of the televised information. The color section contains the circuits necessary to reproduce the color of the televised signal back to the proper hue and saturation. The synchronization section contains the circuits required to properly scan the image onto the inner surface of the CRT. The high voltage section provides the high DC voltages required to make the cathode ray tube function properly. The CRT, or cathode ray tube, is basically a specially designed vacuum tube which has the ability to momentarily store energized phosphorus particles. When scanned properly, these particles will form an image on the face of the tube. This concludes the video portion of your lesson on Part 1, Intro to TV. At this time, you should stop the video and complete Section G in your student workbook. You should review this video often to maintain your new level of understanding on television theory.